Welcome back to another session of Physical Sciences. And as you know, when you see me, we're doing chemistry. Today we will be looking at acid and base reactions, but we will specifically start with chemical equilibrium in acid-base reactions. Before we start, I would like to leave you with a little question that you can think on while I'm busy. Why do people rinse their hair with a dilute solution of vinegar from time to time? Why do we have that need? Think a little about that, and as we go on, you might figure out what the reason for that is. When we look at the concept map, I just want to show you that we will do some autoionization in water. We will discuss Kw value, Ka value, and Kb values as we go on. Right. Okay, the terminology that we should be open for during this lessons or for the next session is acid. What is an acid again? We've learned that the Lorry-Bronsted model says that an acid is a proton donor. In other words, a substance that will give away a hydrogen ion during a reaction. A base on the other side is a proton acceptor. In other words, it will accept or take in a proton during a reaction. Then we will work with ampholyte and we will talk about equilibrium constant, and I think you will remember we spoke about that one, Kc. Right, when we look at the autoionization of water, this is a reaction in a closed system. Remember, we are talking about chemical equilibrium here. It's a closed system. And I want you to know that we're doing this at a constant temperature of 25 degrees or 298 Kelvin. When water reacts with water, it will form hydronium ions and hydroxyl ions. So this is the hydroxyl ion and this is the hydronium ions. So when we have the autoionization, water in the one instance will be an acid and water in the other instance will be a base. Now we've spoken about a substance that can act as a base and an acid, but we will get to the terminology as we proceed. When water is reacting with water, a proton is transferred from the one water to form an hydroxide, and the water that will receive that proton will become an hydronium ion. And in this case, where water reacts with water, we say that word auto comes from the fact that water is now reacting with itself. That's where the word autoionization comes from. The ionization comes from the fact that ions are formed in this reaction. In this closed system, I just want to remind you again, we've got water. The one that will give away or donate the proton is the acid. The other one that will accept the proton is the base. So in giving away, it becomes an hydroxide ion. In accepting it, it becomes an hydronium ion. Water is what we call an ampholyte, or we say it's an amphiprotic substance. Yes, you've heard about that. That is when water can be an acid or a base. Any substance that can be, in some cases, be an acid, or in other cases, it acts as a base. Such substances are called an ampholyte, or we say it is amphiprotic substance. So we have water reacting with water. We already said a bit earlier, the one water gives away the proton and the other water will accept the proton, being the base. At equilibrium at 25 degrees Celsius, when we have this case, we can go write the Kc value and we will say Kc is whatever we have as a product times the other product, which is our ions. These are our products in this case. And we will say divided by water and water. But we know when we do the Kc expression, we never use liquids because liquids has got a concentration of 1. So we do not have to write the 1 as part of the Kc expression. We can then just say that Kc is then equal to our hydronium ion concentration times our hydroxide ion concentration. In this case, Kc is not just any reaction, but Kc is here the reaction that we have for water reacting with water. So we can change this to be specific for the water reaction. Therefore, we say we don't talk about Kc when we talk about the autoionization of water, but we talk about Kw. And Kw is then now the ionization constant of water. And as we know, Kc, or should I rather say Kw, is only affected by temperature. So, if it is at a temperature of 25 degrees Celsius, it's got a constant, and that constant is my Kw is then equal to 1 times 10 to the power minus 14. And that is, when I look at my Kw, it is the hydronium ion concentration times the hydroxide ion concentration. When we look at the hydronium ions and the hydroxide ion concentration, because we have 2 waters here, we can actually now say, since the one times the other one is actually now leading us to where we can say for 1 hydronium ion or 1 hydroxyl ion, we can actually say it's now the square root of 1 times 10 to the power minus 14, and that brings us to the concentration of either the hydronium ions or the hydroxide ions, and this is only for a solution like water. Remember, water should be a pure substance. So when hydroxide ion and the hydronium ions will then each have a concentration of 1 times 10 to the power minus 7 moles per decimeters cubed. And remember, this happens because water, during ionization, water mostly wants to be in molecule form and not in ion form. That is why the concentration of the hydronium ions or the concentration of the hydroxide ions is so very, very low. And the water molecule, how will we know that water would like to be water? Because more than 70% around us is actually water. And this brings us to our first break. I would like you to take this break, take a sip of something, and see you soon.